conditional expectation for sigma field, conditioning sigma field. We said that if you have a probability space and G is some sub-sigma field, of Fn. So not just a subset, but it has a sigma field structure as well. So it would be equal to F. Then the conditional expectation is of an integrable random variable. Right, that x must be also integrable. So I'm assuming that x is integrable and arbitrary random variable. So I want to define the conditional expectation of an integrable random variable given sigma field. Okay. So this conditional expectation is a random variable. In other words, it's a map from omega, measurable map from omega to R, such that satisfies the following property. Number one is that if you check that this random variable must be a G measurable map. In other words, if you are conditioning with respect to a sigma field given a sigma field, then you know that conditional expectation must be G measurable map, random variable. And the second thing is that if you take any arbitrary G, A from G, a sub-sigma field G, and you integrate the conditional expectation, okay, with respect to dp on this A, this must be same as the integral of x over A. This one. Okay. How did we define it? We basically, proved these two properties when we conditioned x with respect to a discrete random variable. Then we generalized it, that how can we condition a random variable with respect to another arbitrary random variable. And now we are taking it even to a more deep level, okay? How we can condition a random variable with respect to sigma field. Now, as I gave a remark in the end, let me rewrite those remarks. The first remark is that I can define now also the probability of an event given the sigma field. In other words, sigma field is a set of information, okay, about a random thing happening. Connection of substance of omega, it's connection of events, and in the light of all these events, what is the probability of happening of this particular event? Okay. A is not necessarily a part of G. Not to the part of G as well. So how do I define it? So we define that, okay, compute the conditional expectation of the indicator function given the sigma field G. Okay, so that's how we define it. Second, if you compute, for example, the conditional expectation of an integrable random variable with respect to the sigma field generated by that particular random variable, then sigma field generated by another random variable y, okay, arbitrary random variable, then this is same as conditional expectation of x given y. Okay? Because if you remember, how did we define it? We defined it that this is a random variable that is measurable with respect to the sigma field generated by y. Okay, and for any A from the sigma field generated by Y, the integral of the conditional expectation is equal to the integral of the x. Now, what would be the definition of this guy actually? I mean, if you see it from here. By definition, this is also a random variable that is, integrable with respect to the sigma field generated by Y. And for any A from the sigma field generated by Y, the integrals must be equivalent. So, since this integral or this conditional expectation is unique, so these two things can't be, two different things. They must have to be. Say they have to basically, when we'll prove the uniqueness, we'll prove that basically that you have uniqueness. In this case, P almost sure uniqueness. Right? So it's not just exact pointwise uniqueness, it's P almost sure uniqueness. So somehow with this, what do I say? With this equality, I would say that we have already done one example of conditioning an x with respect to a sigma field generated random variable y, because we did one example for this application. Same example would serve as an example for computing the conditional expectation of x given a sigma. Okay? These are the two things that I would like to must basically all the time I have. The key thing that I would like to do today is basically try to take out some of the key properties of the conditional expectation, and let's see how many we can do. This definition of conditional expectation generalizes all previous definitions that you have done. So whatever is true here is true for all kind of other conditional expectations that we define. So we define how to condition over a given, over a discrete random variable, over a random variable, and now we're defining that how to condition or compute the conditional expectation given a sigma. Okay. So here are some of the properties that I am interested in. Properties of conditional expectation, and for your feature, what we call for the feature, I would like to get that you should have all the time these properties and actually try to internalize them. I thought use the proof of all these properties, but these properties will be used again and again in many situations, especially if you are doing things in probability theory, static analysis. So the first property, obviously, that you expect from it is that it must be linear. So in other words, I'm in the same setting that okay, I have omega ft and a g and x is integrable. Okay, integrable, and y is arbitrary. Arbitrary random variable, just any random variable. Okay, so the setting is same. So the first property that we must expect is that the conditional expectation must be a linear kind of a. Okay. Which is seen as of x given g plus conditional expectation of y given g.
So you need integrability of y here.
You need integrability of y here itself. So, okay, so let's assume three things.
X, y.
Y and maybe we'll need v as well. So let's put it c as well. So all three are integrable. And this equality holds P almost surely. Okay, so it's not a kind of a pointwise equality, but it's P almost surely equality because these I'm treating this and this as a map actually. So that's a function. That's also a function. So if these two things are equal, they have to agree on each omega, because what is the domain of definition of this function and this function? As a function, it's omega because they are random variable. And what I'm saying is that they are equal P almost surely. In other words, for the omegas for which this is not true, has a probability 0. They are kind of unsatisfactory. Okay. How can I show it? It's pretty simple. Okay, shall I list the properties and then? Well, that's the first property. The second property that I would like to prove is basically that the conditional expectation of the conditional expectation of G is equal to expectation of X. So the average of average is average. The third property is that if Z is G measurable, by the way, this integrability is in the sense of omega fp. So all three random variables are measurable with respect to this sigma.
Yes.
So it's not necessary that they are also measurable with respect to
G.
Gi. So if Z is a random variable that is measurable, G measurable, okay, then the conditional expectation of, say for example, XZ given G is same as Z times the conditional expectation of X given G, we are almost sure. So this property is called taking out what is known. Taking out what is known. So in other words, when Z is measurable with respect to G, so G contains all information about Z actually. So Z is known in G. So somehow you are pulling out that thing out of expectation, something that is known. So that's a property. The fourth property, I'm using a different notation than what book is using in xi, eta, zeta, beta. Xi, I'm using x, y, z. Second thing is that if X is independent of G, so in other words, that if X is independent of G, then the conditional expectation of X given G is same as the expectation of G. And obviously, P almost sure. Everything is P almost sure.
Sorry, dependence. Mean.
So, by I mean when X is okay, basically. What is the meaning of a random variable being independent of G? You can guess the definition. What do I mean by that? Then take any A from G and take any Borel set and consider the inverse image of this B. Okay? Then these two things are independent of each other. In other words, this sigma field and the sigma field generated by X are independent of each other. So we have defined that what is the meaning of two sigma fields being independent. Okay, take any two events out of the, and they are independent. So that's what I mean. If X is independent of G, then the conditional expectation of X given G does not depend on G, just simply the conditional expectation. Something that you can expect for example. You also do this in probabilities. Probability of A given B is probability of A if A is independent of B.
Taking out what is
If H is a sub-sigma field,
I hear the same.
H is a sub-sigma field of G.
Say yeah.
Then I can compute the conditional expectation of x given probability. That's a random variable. Now I want to compute the conditional expectation of this random variable given the subsigma field H. Okay. So this property says that this is same as simply compute the conditional expectation of x given H. Okay, this is we almost surely, and this is called tower property. So you have the tower of conditional expectation. You can simplify this tower of conditional expectations. You'll be almost sure. Because that's a random variable, that's a random variable, these two are maps from omega to r. So if I'm saying that these two maps are equal to each other, so if I'm not writing this, what I'm gonna mean is that no matter what small omega you take from capital omega, these two maps are going to have the same value of that omega. Okay? But this is not the case. You can find the omegas for which these two maps have different values. But the collection of all such kind of omegas for which you have these two maps giving you different values has a value 0. Here, so treat conditional expectation not as a number but as a map from omega to r because it is a random variable. That's what the definition is. Okay. So this is called the tower property. You have a conditional expectation and you want to compute the conditional expectation of the conditional expectation in this small chunk. This is same as that you simply compute the conditional expectation of x in this small chunk. That's it. That's fifth property, and the sixth is that if x is non-negative, then as the expectation, conditional expectation goes to non-negative. Okay. These are the properties that I'm interested in proving it. It's not take more than 10 minutes to prove all these basic properties. Maybe we can begin from the first part. The proof for the first part. Help me out for the first one. If I would like to show that these two things are almost surely equal. Maps are almost surely equal. What should I prove actually?
Consider the set of all those omegas for which this is not true. And show that the set has measure 0.
Okay. But we have also proved something. We have proved. By the way, roughly, what would be L1P? What would be L1 spacer?
So absolute.
So it's a collection of all random variables on omega of p such that the integral of x with respect to p is finite. dp is finite.
Say.
This is what. Because expectation of x is finite.
Say.
Is it making sense? And I know that I know what. It's not a kind of a convergence. If something is true in L1, it must be true in L2. Okay. Let me write a direct argument. Okay. Yes, the argument that I would like to use is this. That if the integral of a function with respect to measure over a set is 0,
then the function
then the function must be 0.
almost surely.
Almost sure.
Say.
It's going to be almost sure. So what I want to do, I want to compute the integral. So let me take an arbitrary b from g.
Say.
Okay, that doesn't have a necessarily, probability measure 0. And let me compute is the integral over p of the one side of it. So it's the conditional expectation of ax plus by given g with respect to what?
P over B.
Over b. Okay. Now, by definition, second part, that if you compute the conditional expectation of any random variable, over a b that is measurable set, then this is same as computing the integral of
Ax plus By.
ax plus by with respect to what?
B.
Okay? Is it making that? And I know that this guy is linear, so this would be same as a times x p plus b times y. Can you see where I'm heading?
Both about English. First circle.
I now return back, and I can say that again by the second property of the definition, this is same as the conditional expectation of x given g over b
Plus
okay, dp plus b and the conditional expectation of y
y
given
given G dp.
g dp over.
Okay, so
And then I can combine them. Okay, so I can write that over b I have this a times, the conditional expectation of x given g
plus B
plus
times.
b times conditional expectation of y given g and d. So you have this equality holding for the integral, and now I'm saying that take the difference of both. So the difference is equal. So if the difference is equal to 0, then the integrand would be almost sure to true. That's what we wanted. Okay, so the trick is this, and this is a good trick. We're going to use it all the time, basically. That if you want to show something, be almost surely show that. If you want to show an equality, we almost surely show that they are different, the integral of their difference is 0 actually. Okay, and then you're gonna have the consequence. The kind of things that you should ponder yourself, because this is a good opportunity to practice the things that you have learned actually. Okay, for now. Second property is trivial. It's very trivial. Why is trivial? To see the definition of the conditional expectation and give me the proof of the second problem. I don't need to do anything. Just have to look at the definition.
Integral property.
Okay.
Almost surely नहीं है ना sir.
Everything is almost sure.
फिर तो property 2 use करते
So the integral of any for any a and g, the integral of the set would be the property that we have axiom number 2. So we'll take
What did I do?
take the a set as the space.
Yes, what you have to just do is that just take A as the entire space actually. You got that. Okay. So the second property is pretty trivial. You just take that entire space and then just apply the second property to get what you want actually. In order to do the third property, I'll do the first part and the rest of things you have to do for yourself. I'll start with, imagine Z is the indicator function of A. So what I want to show that something that is measurable in a given sigma field, you can just pull it out of a conditional expectation. So let's begin with the conditional expectation of Z being an indicator function where A is some function. I hope that you can already guess the argument that okay, if it is true for simple function, it must be true for if it is true for indicator function, it must be true for simple functions, it must be true for positive functions because you can approximate negative measurable maps as this as the sequence of increasing function of simple functions and use monotone convergence theorem. Write the rest of the proof for yourself. I'll just go for this first part. We have enough time for class. Okay, so let's see that why I can pull out the indicator function out of. And how I'm going to show it? Again, the same strategy. If you want to show the equality, take their difference and integrate it. Or take one side, integrate it. Can you get the integral of other side? If this is true, then you can get rid of the integral. Let's start with for any b from g. Let's start with the integral of indicator function of a multiplied by
X.
the conditional expectation of x given g for example. Okay. Obviously, this is same as integrating the conditional expectation x given g over dp on a intersection b. Okay. Or integrate this on b, same as integrating the conditional expectation over a intersection b. But since a intersection b is measurable set, why? Because a and g both are measurable. So this is same as integrating a over a intersection b, what? X db. Okay. And if this is the case, then I can return back. I can say that this is same as b indicator function of a multiplied by x and. Okay. And I can return back and I can say that this is same as the integral over b of the conditional expectation of the indicator function multiplied by x given g dp. And we are done with the proof. Okay. So now we can finish it for yourself that. Okay. Yes. Okay. Now done with the proof. So in other words, next you have to take x to be a simple function. Just writing it ai indicator function of ai are equal to 1 to n. So it's like complete this proof actually. Complete the proof. So it's going to be a very beautiful like this. You don't have to do as much. So complete this proof. And do this for any in general, any random variable. Random variable. Fourth part is that x is independent of g, then the conditional expectation of x given g is expectation of x. Here's the thing. Since x is independent of g, then for obvious reason, for any a in g, the indicator function of a and x are independent. Okay. If you are not sure about it, verify. It's a very simple fact. That if x is independent of the sigma field g, take a set from that given sigma field g and prove that the indicator function of that set and the random variable x must also be independent. It's just restating the definition. It's the same, saying the same things there. Now, if this is the case, then integrate over A this conditional expectation basically. The integral of x. Okay, I can integrate it. That is a T. And this will be same as